So we're looking at that stuff that you've been doing with sine and cosine functions, and then some applications of that. Applications of sinusoidal functions will be anything that follows this kind of pattern of repeating over and over. So things like a Ferris wheel, because it's going around and around and around. This is a problem that used to come up all the time in the departmental exam. There was like always a Ferris wheel question, but it's not as predictable anymore as it used to be. I used to tell students, guarantee these will be on the departmental, but now it's changed. But there still could be. The Ferris wheel is a really common one because it's fairly easy to understand. Some of the other types of applications you could have, if you think of anything that kind of cycles through and does the same thing over and over again. So we talk about weather as an application because every year, this time of year, it gets cold, and then it gets colder, and then it gets warmer, and warmer, and then colder again, and it's a cycle. And you'll see there are some other ones as well that we'll do. But this one's about a Ferris wheel. A Ferris wheel has a diameter of 30 meters with the center 18 meters above the ground. It makes one complete rotation every 60 seconds. Draw the graph of one complete cycle, assuming the rider starts at the lowest point. So what we're going to do is actually make a little table of values. And I'll just do that over here. This is going to be the time, which is measured in seconds, and this is going to be the height, which is measured in meters. So we need to think about that Ferris wheel at time 0, which is when they start, when the person first gets on. How high above the ground are they? 3 meters is how far they are at the beginning, because this distance from the center to there, where they get on, is 15, but the center is 18 meters above the ground. So that's the extra 3 meters. It says it makes one complete rotation every 60 seconds. So if this thing starts spinning, so you get on here, and then it starts spinning, where's the next spot that it's easy to tell how high the rider is? The very top? What about here? Yeah, the middle. How high would they be? 18. And how long would it take to get there? If it takes 60 seconds to go all the way around. 15 seconds. And then the next one, we'll look at the very top. That would take 30 seconds. And what's the height then? 33, because it's 30, the diameter of the Ferris wheel, plus those 3 meters at the bottom, where they like climbed up to get onto it. So then we can continue this and probably look at 45 seconds and 60 seconds. What would the height be at 45 seconds? Back down to 18, and then at 60, back down to 3. And that's one complete cycle, because they start out at 3, all the way up to the top of the Ferris wheel, back down to 3. If you have a table of values, then it's fairly easy to draw a graph, right? You just plot the points. So we'll do, I only need the positive quadrant, because we're not going to have negative time or negative height. And maybe we'll go, let's see. By fives, 5, 10, 15, 20, 25, 30, oops, that's 25, 30, something like that. So 33 would be a little higher than that. And then for time, we might as well break it down into 15-second intervals. 15, 30, 45, and 60. The thing is, you want even intervals, right? Don't go up by the steps of your height. Like, I'm not going to go 3, 18, 33. I want even intervals. So I'm going 5, 10, 15, 20, 25. or you could go 10, 20, 30, or whatever is going to work for you. Even intervals. And then I can start plotting those points. So I could say 0 and 3. Well, that's going to be... I made an arrow again. So there's that first point at 0 and 3. The next point is going to be at 15 and 18. So around there. And then at 30 and 33. 45 and back down to 18, 60, and 3. So the points are approximately there. I'm just going to move that one over a bit. It's not quite in the right spot. And you can see the shape that this is making. So I'm going to join those together and then I'll have plotted that full cycle. It looks kind of like a part of a sine function. It's not a perfect drawing by any means, but it gives you the idea. So what's going to happen is then once you get to that 60, it's going to do that same thing again and again. But it only asks for one cycle, so that's what I'm going to draw. And then we need to write an equation. It says to write the cosine equation of the graph. So that means our equation is going to be something like y equals a cosine b x minus c plus d. And we need to figure out what a, b, c, and d are. Do you remember what a represents? Vertical stretch, or the amplitude. So what's the amplitude of that graph?
30. Or 15.
15, right? Do you remember what b is? It has to do with the period, right? It's not just the period, but it has to do with the period. 2 pi over b is equal to the period. So we need to think about what's the period of this function. 60 seconds. So period equals 60. And that's equal to 2 pi over b. So b is equal to 2 pi over 60, or pi over 30. The period is always equal to 2 pi over b. So 60 is equal to 2 pi over b. Solve that for b. So this. Multiply by b, divide by 60. You get b is 2 pi over 60, or pi over 30. That looks a little different than what you're used to having for a period. The ones we were looking at yesterday all had a number, but this one has a pi in there. That's okay. And now we have to figure out the phase shift and the vertical displacement. And because this is a cosine function, do you remember where we look for those? The middle below the maximum, right? So we're going to look right in here at that point that's halfway between the maximum and minimum and directly below the maximum. So vertically it's halfway. It's along that kind of central axis of the graph, which is here, and it's directly below the maximum. If we can find the coordinates of that point, then those are our c and d values. So the coordinates of that point, well, the x value will be the same as the x value of the maximum, which is, or the t value in this case, with the way that I have it, but will be 30. And the y value is this value here, 18. 30 and 18 are the coordinates of that point. That means 30 and 18 are the c and d values. So x minus 30 plus 18. Once we've come up with that equation, put it in the calculator, we know that it's correct because we got the same graph on the calculator as the one we sketched here. We can answer part C and D. What is the height of the rider at 52 seconds? How are you going to use your calculator to answer that? Trace, or probably second trace if you're on an 83 or 84. Value, fill in 52. You can do that on the Inspire, but it's a little bit different. You should end up with, for C, X is equal to, or sorry, Y is equal to 7.96. So for part C, 7.96 meters, and you're just using your calculator to do that. The other thing it asks you is, at what time is the rider at 20 meters? So to do that on your calculator, you're going to have to go into y equals and graph y equals 20. And then find the intersection points. And there's going to be two spots where the rider's at 20 meters. Because it's going to happen around here and here, like those 2 points on your graph. There and there. So find those 2 points of intersection on your calculator. You should end up with 43.7 seconds and 16.3 seconds. The earliest sunset occurs at 5:34 p.m. on December 21st, and the latest at 11:45 p.m. on June 21st. Then it says, write the cosine equation of the graph. Draw the graph approximating the sunrise times throughout the year. What is the sunset time on April 6th? And then it asks about what percentage of the year is the sunset time earlier than 8 p.m. So we're going to start by making a table of values and sketching a graph. It's easier to do that than to try to go straight to the equation. But we only actually have two values for our table of values. What are the variables here? We have the day and the sunset time. Day and time. So we have the earliest sunset is at 5:34 p.m. on December 21st. We need to take those values and switch them into numbers that we can plot on a graph. So that's why I had listed the number of days in each month, because I want to find out December 21st, what day of the year is that? First day, second day, third day, fourth day. December 21st is day 355. And then we have 5:34 p.m. That time, 5:34 p.m. is minute 334 of the day. Take 5 hours. Oh, that's not right, is it? No, what's wrong with it?
12 hours?
That's would be 5:34 a.m. So how do I get the time of 5:34 p.m.?
It's 17:34.
17:34.
You kind of got to think military with this.
Mm-hmm. So you add another 12 hours to that, right? Which is another 12 times 60 minutes. 1,054, because it's 17 hours multiplied by 60 minutes plus 34 minutes. 1,054. I think the last time I did this in hours instead of minutes. But whatever, this will still work. I want to see how it turns out, so we're going to keep it this way. The other point that we have is June 21st. What day of the year is that? Adding up all the days to there gives us 170, day 172. And it says that it's at 11:54 p.m. And that's minute 1434. 14:25. Holy smokes. I don't know if you guys should trust anything I say today. 14:25, because I read it as 11:54, not 11:45. $100, $200, $300. For days, 400. And then for time, let's do 500 and then 1,000, 1,500, 2,000, and then 2,000. So when I go to plot the points, I go to day 355 and 1054 and then 172 and 1425, and all I end up with is that. That's the only information it gives us, right? Well, almost. The other thing that it gives us is that one of those is a maximum and one's a minimum. And so because I know that, then I can figure out what the graph actually looks like. This is a maximum point and this is a minimum point, and the graph's going to continue kind of like that. If I didn't know that it was a maximum and minimum, 2 points wouldn't be enough. But because we do know, then it is. To write the equation, we need to look at what is the amplitude of the graph, what is the period, the phase shift, and the vertical displacement. Amplitude, if we look at the maximum, subtract the minimum, divide by 2. You guys better help me with this because I'm having a lot of trouble today. So we're going to take, what's the maximum value? The maximum y value? 1425. Subtract 1054. And then divide by 2. 185.5. Yeah? Okay, good. Phew, maybe I'm back on track. We need to find the period. What's the period of this? 365, right, because it's a full year, right? So B is equal to 2 pi over 365. 2 pi over the period. And then we need to find that point. It's asked for a cosine function, so we're going to look for a point that is right along that middle line and below the maximum, so like there. We need the coordinates of that point. So the x-coordinate, that's easy when it's a cosine function, because it's the x-coordinate of the maximum. So it's 172. But what's the y value there? 1054 plus 185.5, yes. So it's 1239.5. Those are your C and D values. So now we have A and B, C and D, and we can write the equation. Y equals 185.5 cosine 2 pi over 365 x minus 172 plus 1239.5. Once you have that graph on your calculator, you can use the calculate function, which is second trace on the 83 or 84, to find out the other things that we want to know. So it asks, what's the sunset time on April 6th? We need to figure out what day of the year is April 6th. What is it?
96.
Day 96. So then you can use your calculator, second trace value, put in 96, and it gives you 1287.63. Is that what yours gave you?